contour plot and regular plot down. Next thing we want to look at is how do we return to this question of finding maximum and minimum values, and that's where we're going to run into this notion of a partial derivative. And let's go back and consider this first function, and we'll take this contour plot. And what we're going to do is we're going to try and isolate what we see on these walls through a partial derivative, either with respect to x or with respect to y. And essentially what that means is where we're kind of standing and looking at the function from, what our perspective is. We're going to freeze everything else and just let x be that thing that changes, or y be that thing that changes. So in this function, we're going to write this as the partial derivative of f with respect to x, and we're also going to find the partial derivative of f with respect to y. So by hand, again, we just hold everything else, we treat everything else like a constant except for those things that have x's in them. And the derivative of constants are 0. So 9, that goes away. Derivative of negative 2x is just going to be negative 2. This 4y goes away, of negative x squared is negative 2x, and this 4y squared goes away because, again, these are just treated as constants. And similarly, when we take the derivative with respect to y, again, our constant goes away. This is just a constant. We've got 4y, so that's derivative 4. Negative x squared goes away. Negative 4y squared, we get negative 8y. Okay, so there's our two partial derivatives. All right, now if we want to find those using the computer, this is where things maybe can get a little bit awkward at first, because we're going to have to switch between numpy and sympy when we're doing this. If we want to find these derivatives, we were just working symbolically rather than numerically, so we have to, make sure that x and y are in here as symbols. Okay, so let's go ahead and do that though. We have our function defined as f. All right, we'll go ahead and then go ahead and define symbols x and y. And then I can take a derivative of f of xy with respect to x. And I get negative 2 minus 2, same thing here. I could also take the derivative of f of xy with respect to y, and I get 4 minus 8y. All right, well, so what? Well, remember, if we wanted to find a maximum or a minimum value, what we did was we tried to identify where that first derivative was equal to 0. Now, the partial derivative of f with respect to x, when does that equal 0? Well, it looks like at 0. The partial derivative of f with respect to y equals 0 at about y equals 2. So if we return to this kind of contour plot, we can see that in the x direction, these maximums are occurring here at about 2, and in the y direction at about 0, other way around, 0 and 2. Okay, but that's essentially what we're doing. We're like freezing our perspective and finding where the maximum or minimum value of what we're projecting onto one of these walls, where that occurs. Now, again, the other thing is that we're working symbolically here. In the first example, it doesn't matter too much because we have polynomials, but in the second example here, where we have a cosine, if we want to plot and then use derivatives, we're going to have to use two different versions of this function. One with numpy for plotting, but taking derivatives, we want to change this to sympy so that we can take partial derivatives. So let's do the same thing here and find derivatives of this, and then we can verify those on the computer. So let's just erase that. And okay, so our function was g of xy equals y squared minus 2y, the cosine of x. Okay, so the partial derivative of g with respect to x, we're going to treat everything else as a constant, so that means this goes away, and we're just taking the derivative of the cosine of x. Derivative of cosine is sine, is negative sine, so we get 2y times the sine of x, and the derivative of g with respect to y, everything else is a constant, so then we have y squared, that's going to be 2y, and minus 2y, right, so that will just be minus 2 cosine of x. Okay, and again, if we want to use the computer to verify this, we have to change this numpy to sympy. Okay, and then we can do the same thing. We'll take the derivative of g with respect to x. We get 2y sine x, just like we did by hand. And we take the derivative of g with respect to y, and we get 2y minus 2 cosine x. All right, but that's the kind of what a partial derivative means visually in 3D. It means we're just kind of freezing it from one of these perspectives, either the x or y. And practically how we find those derivatives, we just do like we've done before. We treat everything else as a constant though.